Hello, good afternoon, everyone. Okay, so let's start today's tutorial. So today we will talk about the homework 2 solution. So this is question number 1. By the way, I'm going to give you only the high-level description. So some details could be missing, and then please complete the details. Yeah, make sure that you understand everything completely. So the first question is about throwing two distinct dice, and then we let AR to be the number of ways where the sum is R. But we have a restriction. We require that the first die gives us an even number, and the second die gives us an odd number. We want to count the number of ways, so it is unrelated to probability, so don't worry about this. And then we want to find out what is the generating function for the sequence A0, A1, A2, blah, blah, blah. So it is actually fairly simple. So it is this one. So to get the generating function of the whole system, we get the generating function for the first die multiplied with the generating function of the second die, and that's it. So for the first die, there is something wrong here. I'm sorry. Okay, so there should not be a 1 here. So there is one way that we can get a result of 2. There is one way that we can get a result of 4. There is one way that we can get a result of 6. So the generating function for the first die, yeah, forget about this one, should be x squared plus x4 plus x6. And then for the second die, it is x plus x cubed plus x5. And then you can do actually one more step. Okay, so you can take out the common. So you can do factorize. This is not. So you can take out the common factor. So after simplification, you will be able to get something like x cubed multiplied with 1 plus x squared plus x4 to the power 2, something like this. But in any case, yeah, if you can write down something like this, this is already perfect. Now the second question is, we are supposing that we have n distinct objects, and then we have 3 colors to be used, and then we want to find out the number of ways to color the objects. But then we have a restriction. We require that each color is used at least once. So how do we do this? Okay. So there are actually 2 ways to solve this problem. The first one is, yeah, we can use the principle of inclusion and exclusion. So first of all, let us try to find out the total number of ways of coloring when there are no restrictions. So we have n distinct objects, and then we have 3 colors, no other restrictions. So in this case, because each object we can have 3 ways to color, so there are going to be 3 to the power n. But then for this counting, we have overcounted several number of cases. For instance, we have not considered some color is not being used. So instead of this, so we want to deduct the case that a certain color is not used. So the number of ways that a particular color, let's say the red, is not used will be 2 to the power n. But then there are 3 different choices for the color that we are not using. So they are going to be 3 times 2 to the power n. So we should deduct this number of ways from the overall number of ways. But somehow we have over deduction because when we are counting the number of ways that we are not using red, there will be some cases that overlaps with the case that we are not using yellow, let's say. So in that case, we should add back the over deducted case. So in that case, we should add back the number of ways that exactly 2 colors is not used. So maybe we are not using red and yellow, so there are how many ways are there? So that means that we are using the third color, let's say green. So there are 1 way of doing so. But then it could be the case that we are not using yellow and green, so we should add this back. And then there is also 1 way that we are not using red and green, so we should add this back. So after this, then we have added back something that we have over deducted. And finally, we may need to add back the case that we have we have what? We have yeah, so, but I think that's overall the case because there's no more case left. So the only case left is we are not using any of the colors. But clearly that doesn't make sense because there's no way of doing so. So in that sense, the inclusion and exclusion principle will give us the result of 3 to the power n minus 3 times 2 to the power n plus 3 times 1 to the power n. But the purpose of this class or this set of exercise is allow you to practice your generating function or exponential generating function. And this is a very good way of doing such a practice. We don't need to know inclusion, exclusion, but what we just need to know is we can use exponential generating function to help us solve this problem. Because this is a permutation problem. So we are going to use exponential generating function. So assume that we are going to find out, okay, so because so one way to represent a particular coloring is we are going to use a string such that the string consists of characters, and each character we can choose from 1, 2, or 3, representing which color the particular object, the cave object or the cave character is colored by a certain number, means that the cave object is colored by that color. So in that sense, we can come out with the permutation counting problem by getting the exponential generating function for the first color multiplied with the exponential generating function for the second color multiplied with the exponential generating function for the third color. And so in general, the exponential generating function when there is no restriction is e to the power x. But since we cannot allow the case that we are not using a particular color, so we should minus 1. So in that sense, the overall system, the exponential generating function for the overall system will be e to the power x minus 1 to the power 3. And this time we can just expand it to get something like this. There's a typo here, sorry. So it should be e to the power 3x minus 3 times e to the power 2x plus 3 times e to the power x. So I will make the corrections when I send the slides to you later, and then minus 1. And once we know the exponential generating function, the required or the desired number of ways is simply we find out what is the coefficient of x to the power n, and then multiply this with n factorial. So from this part, e to the power 3x, it will generate the term 3 to the power n. And from this one, minus 3 e to the power 2x, it will generate the term minus 3 times 2 to the power n. And from this one, it will generate the term 3 times 1 to the power n. And for this one, okay, actually it depends on whether n is equal to 0 or not. When n is equal to 0, yeah, then we should have minus 1. But when n is not equal to 0, then it doesn't contribute to any coefficient of x to the power n. So in that case, it is nothing. Okay, so let's just assume. So actually in the question, we are saying that n is at least 3. So in that case, we don't have anything to consider here. So this is question number 2. Okay, now for question number 3, we want to find out what is the coefficient of x to the power n in this fraction. Now this fraction, we can notice that the denominator is a very nice polynomial. It can be factorized by x minus 3 times x plus 2. So it can be factorized. And then we can make use of the factorization and use the technique of partial fraction to help us solve this problem. So how do we do? Okay. So first of all, this is the standard partial fraction technique. So after factorization, we find that x squared minus x minus 6 can be factorized as x minus 3 times x plus 2. So in that sense, we can actually know that this particular thing can be written as something divided by x minus 3 plus something divided by x plus 2. And the thing here is actually depends on the degree of the polynomial in the above. Because we find that the degree of the polynomial in the above is less than or equal to that of the bottom part, we know that we can find constant number A and constant number B to fit in this equation. So we can solve this easily. So by solving, so how do we solve this? This is easy, because when we are doing the, so when we are retrieving, so how do we do this? So because this is x minus 3, so if I want to make the denominator on the right hand side to be the same as that of the left hand side, we can do so by multiplying x minus 3 with x plus 2 and multiplying x plus 2 with x minus 3. And in that sense, we will see that a times x plus 2 plus b times x minus 3 must be equal to x plus 1. And in that case, the coefficient of x that we have just got must be equal to the coefficient of x here, so it is equal to 1. And similarly, the coefficient of the constant term that we have just computed will be equal to 1 here. So by solving the linear equations, then we will find out that a is equal to 4 over 5 and b is equal to 1 over 5. So 4 over 5 here and 1 over 5 here. And next, we can do something further. Okay. So the next part is, originally it is x minus 3, so intentionally we can change it to 3 minus x to help us use the binomial theorem later. So by changing x minus 3 into 3 minus x, then we multiply a minus to the numerator. And similarly for this one, we change x plus 2 into 2 plus x, so we don't need to do anything. And after that, we want to make the denominator in the form of 1 minus something or 1 plus something. So to do so, we can get it into 1 minus x over 3. So we divide 3 on both sides, so we will get minus 4 divided by 15 here. And similarly, we want to make it into 1, the constant term from 2 into 1. So we divide everything by 2, so the top part becomes 1 over 10, and the bottom part becomes 1 plus x over 2. And then we want to find out what is the coefficient of x to the power n in this one. So it is equal to the coefficient of x to the power n here plus the coefficient of x to the power n here. And it is very simple. So this one will be minus 4 over 15 multiplied with 1 over 3 to the power n. And then for this one, this will be 1 over 10 multiplied with minus 1 over 2 to the power n. And that's simple. Okay, question number 4. Now for question number 4, we want to find the closed form of this expression. Now notice that sum of the parts, so we have a binomial term here. So when you see some binomial term, perhaps we can use binomial theorem to help us to do the simplification. So it is n choose m multiplied with w to the, or omega to the power m, and m ranges exactly from 0 to n. So all the possible binomial terms are considered. So this is actually, this part, the middle part here, can actually be replaced by 1 minus omega to the power n. And after we simplify the middle part, we will see that this is 1 plus omega to the power n, x to the power n, so it's 1 plus omega times x overall to the power n divided by n factorial. And then we're summing everything from n is equal to 0 up to infinity. So it is the exponential function. So it is the exponential function with parameter 1 plus omega times x. So the overall result will be e to the power 1 plus omega times x. Okay, so that's simple. Okay. And now let's go to question 5. And for this question, we want to find the EGF of the sequence 1, 1 times 5, 159, 159, 13, and so on and so forth. There is a hint here. The hint asks us or suggests us to guess the EGF to be of the form 1 minus ax to the power b. Okay, so how should we guess? Okay. So somehow, because there is no strange term like divided by 1 factorial or divided by 2 factorial or divided by, no, it shouldn't be there, okay. But there's no terms such as multiply with something to the power n, multiply with something to the power n, and so on and so forth. Then we will somehow see that the a term that should appear here as a to the power n is cancelled somehow. So why is it being cancelled? It is because of B. So what we want to do here is that when we are doing the guess, we hope to have B having this so B will be a fraction or a rational number that we try to consider such that the denominator of B is exactly A. And next, if you look at the EGF, you will see that there are two numbers that should be quite related. So first of all, the number 4 should be related because it is 1 and 5, 159, 159, 13. So if you just consider each of the numbers here, they form an arithmetic progression with the difference 4 here, 4, 4, 4, 4 here. So 4 seems to be a magic number. And also another magic number is 5 because you intentionally, after doing the expansion, you will get a 5 as the coefficient of x. So it will be becoming 1 plus 5x plus 45 x squared over 2 factorial and so on and so forth. So in that case, you should be seeing 5 somewhere. So this is our guess. So let's try to guess A is equal to 4 and B is equal to minus 5 over 4. And finally, after testing, it works. Okay? So the expression here will be equal to 1 minus 4x to the power minus 5 over 4. Okay, as an exercise, see if you can do something like this. Suppose that this is rather not like 1 and 1 times 5 and something like this, but instead we have 2 times 6 here, and then 2, 6, 10 here, and 2, 6, 10, and whatever. 2, 6, 10, 14 here, and so on and so forth. What would the generating function, exponential generating function be? Okay. Now the constant term, you may think about it. Maybe you can consider it separately. Okay, finally we have a bonus question or a question that doesn't have any points, and then we ask you to study by yourself something called the Ferris diagram or Ferris graph. So let me do a very brief introduction of what it is here. So Ferris diagram is a way to represent an integer partition using dots, such that the kth row is the kth largest number in the partition, and then we assume that all the dots are aligned to the left. So what does that mean? So suppose that we have an integer partition of 12 into 5 plus 3 plus 2 plus 2. So first of all, this is an integer partition. We arrange the numbers from large to small. So you see 5, 3, 2, 2 here. And next, we use the same number of dots to represent the integer here. So we have 5 here. So we have 5 dots in one row. And then the next row, we will have 3 dots. And then the next row, we have 2 dots. And then the final row, we will have 2 dots here. So this is the Ferris diagram to represent the partition of 5, 3, 2, 2 of the number 12. Okay. So what we see is that each of the integer partition will have a unique representation by the Ferris diagram. And then here we assume that we are placing the dots row by row, right? But on the other hand, we can actually read the dots column by column. And if we are doing so, this is like we are also looking at the Ferris diagram. Yeah, flipped, or yeah, it's like the flipped by something like 45 degrees along the diagonal axis. So what do I mean? So in the same example as before, originally row by row consideration, we will have the integer partition 5, 3, 2, 2. But if you look at column by column, it looks like it is 4 plus 4 plus 2 plus 1 plus 1. Notice that if we are doing the arrangement of row by row from the largest to the smallest aligned to the left, then reading column by column, you will see that the largest number will always appear on the left-hand side, and then the numbers will now be in monotonic decreasing order. Okay, so it is also outputting the partition in large to small order. So it is then a Ferris diagram representation, but it is just arranging the numbers from row to row into column by column, aligning to the left into aligning to the top. Is that okay? Now, so what do we see? So we see that a particular integer partition can have two interpretations. If you read it row by row, you will have something like column by column. And using Recurrence diagram, we can show some very interesting results, which is otherwise difficult to show. So for instance, we can show that the number of ways to partition n into k parts must be equal to the number of ways to partition n into parts such that each part do not exceed k. Why? Imagine we are representing a partition of n into k parts using Recurrence diagram row by row. Then if it is the case, then what will happen to the column? So each column will be representing some number such that the value cannot exceed k. And vice versa, right? So in that case, we just use a one-line proof. Watching a partition row by row means it is a partition of n into k parts, but watching the same partition column by column will give us a partition of n into parts such that no part exceeds k. So that's it. So we can see that this is the correct result. And in the assignment question, we have this question. So we want to find out how many ways to partition the number 2r plus k into exactly r plus k parts. So let's imagine. So we are getting a number with, so let's imagine we have a total number of 2r plus k dots, and then we are dividing into r plus k parts so that what? So that we are using the Recurrence diagram to place them. So in that sense, what do we see? We will see that the first column, so this is the row by row view, okay? We will see that the first column must always be filled with exactly r plus k dots. Yeah, because it is exactly r plus k parts. So because they are exactly r plus k rows, right? So that means that the first column must have exactly r plus k dots. So the remaining graph here that we see will be what? We'll be having exactly r dots. Okay, and we want to find out how many ways to partition the number. So you can see that as long as we get a particular partition of r for the remaining dots, when we combine this one with extra dots on the left-hand side, yeah, for r plus k of them, so we have a partition of r in any way that we want, and then we combine this with the first column that has r plus k dots, then this gives us a partition of 2r plus k into exactly r plus k parts. So the answer for this question is, it is the same as the number of ways to partition the integer r. So interestingly, what does that mean? So if this is the way that we are requiring to do the partition, then the number of ways to do this partition is independent of k. So the number of ways to partition 2r plus 1 into r plus 1 parts is the same as the number of ways to partition 2r plus 2 into r plus 2 parts. It is the same as the number of ways to partition 2r plus 1 million into r plus 1 million parts. So it will be always the same as the number of ways to partition r. Okay, so I hope you like this this topic, Recurrence diagram, and then yeah, please visit the Wikipedia page or any other related web page that has an introduction to this one, and then study it by yourself. Okay, so that's all for what I want to say today, but let me quickly take a look if you have any question. Okay, so let me see. Okay, good, very good. So I see that Robin mentioned that he has another way to solve the exponential generating sequence problem. Yeah, that's good. Okay, so as we don't see any questions so far, so that's all for today, and then we will have the class summary on Thursday as usual. And remember that we will have exam 1 next Tuesday. Okay, good luck and see you soon. Okay, bye bye. Yes, we will try. Thanks for asking. So our tutors will try to mark their homework as soon as possible. I really hope that they can finish it as soon as possible. At least homework 1 is now ready, I guess. Yeah. Sorry for the delay. Yeah. Okay. Okay, that's all for today. Thanks.